Educational Module, Machine Learning, Learning Unit, Core, Unsupervised Algorithms. Clustering algorithms are categorized based on the following criteria. Input data type, numeric, categorical, textual. Input data size, algorithms like BIRCH, DBSCAN and CURE. Algorithmic implementation. When it comes to algorithms, there are partition centroid-based clustering, hierarchical clustering, density-based clustering, probability distribution-based clustering, fuzzy clustering, subspace clustering. Evaluation. The quality of the produced clusters is evaluated based on the intercluster and intracluster distances. Clustering can achieve very high performance on data that are already somewhat grouped and not smeared. The scalability of an algorithm is important. Large data size. A set of algorithms are specifically designed for large data sizes and can work with limited memory. The subset of the data is iteratively loaded in memory in order to perform clustering and is then combined with the results of previous executions. Euclidean distance is very popular for continuous numeric data. It is calculated as follows. The cosine similarity is popular for categorical data. Finally, the Jaccard similarity is popular for categorical data and accounts for the local quality of the cluster. K-means is one of the most common clustering algorithms. First, the cluster centers are selected randomly. Then, each object is assigned to its closest cluster center and the cluster center is recalculated. The whole process is done iteratively and stop when the cluster assignments do not change significantly. K-means attempts to minimize the squared deviations and as a result is considered a squared error algorithm. Step 1. Initialize cluster centers randomly. Step 2. Compute the distance of each object to each cluster center. Step 3. Assign each object to the cluster that it was found to be closest to. Step 4. Compute the new cluster centers. Step 5. Repeat steps 2 to 4 until cluster assignments remain unchanged. The time complexity is OKN, where K is the cluster count and N is the object count. The Euclidean distance is calculated as follows, and the goal of K-means is to partition it into K clusters such that each point in a cluster is similar to points from its own cluster than with points from some other cluster. The main advantages are the convergence speed and the simplistic nature of it. The main disadvantages are the following. It is sensitive to the choice of the initial cluster centers. The number of practical heuristics have been developed. For instance, one could randomly choose K-points from the given dataset as cluster centers. Other methods try to pick K-points from X which are farthest away from each other. The number of clusters must be explicitly set by the user. It makes a hard assignment of every point to a cluster. It doesn't work for categorical data. Because of these reasons, many variations of K-means were created. Fuzzy C-means aim to extend the traditional K-means algorithm with the help of fuzzy logic theory. Each data point can belong to more than a single cluster, which is different than what K-means was attempting along with a different objective function as well. Fuzzy C-means belong to fuzzy clustering. Step 1. Choose a number of clusters and assign coefficients randomly to each data point that measure the degree of membership to each one of the clusters. Step 2. For each data point, compute its coefficients based on a function. Step 3. Compute the cluster centers while aiming to minimize an objective function. Step 4. Repeat steps 2 to 3 until the algorithm has converged. Little change between two iterations. Objective function, where xi are the elements, cj are the cluster centers and weak are the coefficients. Soft clustering. Fuzzy clustering is also known as soft clustering. It is worth noting that it generalizes the notion of a partition, in the same way that a probability estimator generalizes a classifier. K-methoids, also known as PAM, is a clustering algorithm directly related to the K-means algorithm. Both the k-means and k-metoids algorithms are partitional and both attempt to minimize the distance between points labeled to be in a cluster and a point designated as the center of that cluster. However, contrary to k-means, k-metoids chooses data points as centers metoids instead of only minimizing the Euclidean distance. Each cluster is represented by a single metoid. It uses a greedy search which may not find the optimum solution, but it is faster than exhaustive search. Step 1. Randomly select k of the data points as the metoids. Step 2. Associate each data point to the closest metoid. Step 3. For each metoid data point m and non-metoid data point n, swap them, associate each to the closest metoid and recompute the cost. Step 4. Compute the total cost of the configuration for all the possible pairs between data points. Step 5. If the total cost increased in the previous step, undo the swap. Step 6. Repeat steps 3 to 5, while the cost of the configuration decreases. Positives. It is more robust to noise and outliers because it minimizes a sum of pairwise dissimilarities. It is not affected by order of input. The main negatives concerns its scalability. Clara clustering large application applies k-metoids PAM on multiple subsamples, keeping the best result. CLAR dense clustering large applications based on randomized search applies k-metoids on the entire dataset, but only explores the subset of the possible swaps of metoids and non-metoids. Traditional clustering algorithms such as k-means have big drawbacks when it comes to large databases. The running time can be very high, and given large differences in geometries of different clusters, the square error method could split these clusters, which is often a mistake. Algorithm must run/scan through the data just one time. It must work on the memory and with memory limitations. It must be incremental. The algorithm has to read a subset of the data into the memory and combine the results with those of previous subsets, thus incremental. Birch balanced iterative reducing and clustering using hierarchies is algorithm used to perform hierarchical clustering over particularly large datasets. It is able to incrementally and dynamically cluster incoming, multi-dimensional metric data points in an attempt to produce the best quality clustering for a given set of resources. It exploits the observation that data space is not usually uniformly occupied and not every data point is equally important. The grouping information is stored in a CF tree, where each element refers to a single cluster. New nodes are inserted to the tree constantly. Step 1. Build a CF tree out of the data points. Number of clusters is defined by the user. Step 2. Scan all the leaf entries in the initial CF tree to rebuild a smaller CF tree, while removing outliers and grouping crowded subclusters into larger ones. Step 3. Hierarchically cluster all leaf entries. Step 4. Optionally redistribute the data points based on the clusters obtained from Step 3 and optionally discard outliers. The algorithm. The main positives are, it runs/scans through the data just one time. The user-defined cluster count. It can handle outliers better. It operates well under memory and time constraints. It faster than other clustering algorithm on big datasets. It is incremental. The negatives are, it only works on numeric data. It has bad performance when faced with unconventional non-spherical cluster shapes. Each node can only include a certain number of data points. The problem with the Birch algorithm is that once the clusters are generated after Step 3, it uses centroids of the clusters and assigns each data point to the cluster with the closest centroid. Using only a centroid to redistribute the data has problems when clusters lack uniform sizes and shapes. To avoid the problems with unconventional cluster shapes and sizes, pure clustering using representatives was created, which employs a hierarchical clustering algorithm that adopts the middle ground between the centroid-based and all-point extremes. It utilizes partitioning of the sample data as well as random sampling. Time complexity is this, where n is the number of data points. The algorithm of CURE. The positives are that it is not sensitive to outliers. It can identify unconventional non-spherical cluster shapes. It can be combined with sampling and other techniques. DBSCA and density-based spatial clustering of applications with noise is a density-based clustering algorithm. It requires two parameters, BPS, which is the maximum distance between two samples for them to be considered as in the same neighborhood, and MINS, which is the minimum number of points required to form a dense region. The time complexity is this, where n is the number of data points. Step 1. Find the points in the ETS neighborhood of every point, and identify the core points with more than MINS neighbors. Step 2. Find the connected components of core points on the neighbor graph, ignoring all non-core points. Step 3. Assign each non-core point to a nearby cluster if the cluster is an ETS neighbor, otherwise assign it to noise. The algorithm. The main positives are: it can find non-linearly separable clusters. It is not affected by outliers. It can find arbitrarily shaped clusters. It requires just two parameters, which can also be set by a domain expert. The negatives are: it relies heavily on the EPS and MINS parameters. It suffers from hierarchical algorithm-related problems. It cannot use sampling and cannot cluster datasets well with large differences in densities. Finally, the quality of clustering depends on the distance measured, which is a problem for high-dimensional data.